Students, welcome to lecture number 8 on this course on AI/ML in materials engineering. So, we will be talking about mostly how the mechanical properties can be measured in this lecture. Before that, we will do some recap as usual for every lecture, and basically what we are discussing here is this tetraden, what is called materials tetraden, and the material tetraden talks about the correlation between processing, structure and properties. As you can clearly see here, the processing is done here, that is related to the properties via structure, and these properties actually dictate the performance of any device or any kind of system which you are going to make using this kind of materials. At the center of this tetraden, we have also placed something known as a characterization, because structure can be only determined by using characterization techniques. That is exactly what we do by using or employing different kinds of characterization techniques. We determine the structure at different length scales and then correlate that with the properties. So, that is the basic aspects we have been discussing for so many lectures, and it will take some more time, but remember this material tetraden very important aspects in the design of new materials or discovery of new materials. Well, few important aspects which we discussed. First, we talked about high temperature metals and alloys, and they are used for jet engines, gas turbines, rocketry and many nuclear applications. Material will require high strength, creep resistance, corrosion resistance. Some of this we will talk about today in the lecture, later part of the lecture, and this will be required at elevated temperature like temperature excess of 1100 degrees Celsius. And in fact, future jet engine will require materials that can withstand above 1400 degrees Celsius temperature. So, we are yet to see those kind of materials, and so that future jet engines can fly with high speed and performance. So, traditionally we use nickel based superalloys for jet engines. The heart of the jet engine is this basically this blades, and these blades are actually made up of nickel based superalloys, and they are basically single crystals. If you understand, I discussed a lot about it. This picture shows you that this is a one single crystal nickel based superalloy. It can contain many elements, as you know, that is why it is called a superalloy. Other than that, we can also have refractory metals which also can sustain very high temperatures like tungsten, niobium, moly, tantalum. Well, ceramics actually are traditionally important for high temperature applications. They are compounds of metallic and non-metallic elements. Go back to the periodic table. The metallic elements are the center part or left part of the periodic table, and non-metallic element like oxygen, carbon, nitrogen, boron, they are on the right side. Boron is on the left side, but oxygen, carbon, nitrogen are on the right side of the periodic table. So, when they react and form oxides, carbides, nitrides, it produces ceramics. Ceramics have very high melting temperatures, and they have a compressive strengths which are much higher than the tensile proper strengths, but traditionally they are very brittle. But some of the ceramics like silicon carbide, silicon nitride or zirconium dioxide consist of little bit amount of yttrium oxide, can provide moderate toughness. They have normally low thermal and electrical conductivities. Well, we talk about little these aspects we discussed, properties of that we will talk about much later of this class, and then we talk about polymers. Actually, polymers actually are very important class of materials which are utilized in many applications, and there are traditionally three types of polymers exist: thermoplast, thermoset and elastomers. And as you know, thermoplast and thermoset actually differ in many ways. I will not talk about details of that which are listed here. Finally, we talked about elastomers. Elastomers actually are rubbers, but they are used in many applications like tires, footwear, gaskets, seals, floorings and many more. Actually, they can undergo large elastic deformation when subject to the stress. They can retain original shape and size on stress removal. They can be blended, or they can be prepared synthetically, or they are available naturally, and they provide all kinds of properties we know like abrasion resistance, corrosion resistance, vibration and shock absorptions, electrical insulations as well as non-skid surfaces. Well, polymers are prepared by what is known as a polymerizations. There can be two types of polymerization, additional or step polymerizations. Polymers means different kinds of mers or similar kind of mer actually are present in large numbers, that is called, this example polyethylene. Okay. Polyethylene has CH4 as the building block or mer. Okay. So, this CH4 is basically what? Basically nothing but the basic building block of the material, and then they are polymerized to produce this chain. As you can see, N can be anything, it can be 10,000, even 100,000 possible also. Step polymerization is used to produce nylon, which is very important polymer. Polymers can be linear, branch, loosely cross linked as well as tightly cross linked structures, and rigidity of the polymer actually comes from the structure. 3D cross linked structure which is tightly cross linked called, they can provide very rigid polymeric structures. On the other, linear or branch one will not be so rigid, they will be softer compared to the loosely cross linked or tightly cross linked structures. Well, the polymers can have one single unit, that is called homopolymer. It can have many units like copolymers also possible, and they can arrange in an alternative fashion or random, or they can be in a block polymers also. Blocks of polymers can be in one place, other place you can have other polymers, or there will be grafting possible also. Grafting you must understand, we always go for grafting when we lose hair, and grafting is basically connecting these polymeric chains with the central chain. Okay, you can see that how grafting is done. Finally, we talked about crystallinity amorphous structures, remember that. So, because polymers have both amorphous plus crystalline portions. Amorphous structures are basically random, and crystalline structures means the chains of polymer arranged in a very nice orderly manner. That is why they are called crystalline structures. In a polymer, both of the things can be present, and we talked about little bit of amorphous and crystalline variation, because you may not understand it completely. In amorphous material you have a completely disorder, there is no specific arrangement of atoms or order present. On the other hand, crystalline materials have grains and grain boundaries, and grains will have order arrangement of atoms, as you can clearly see in this picture or in this picture. So, grains have order arrangement of atoms, and in between the grains you have what is called as a grain boundaries, and these grain boundaries will have haphazard arrangements of atoms or random arrangement of atoms, but not as random as in case of amorphous structures. So, the glass, which is present as a ubiquitous material for us, whether we use specs or we use window glass or any other glass, has actually amorphous structures, and because of that it can only transmit light, because there is no grain boundaries. That is the primary reason why light can pass through these glass structures. One can look through this book by Michael Aspey, much detail available. This is very interesting book which can provide you perspectives of all kinds of materials in nano domain in the history. So, amorphous structures are very prevalent in polymeric materials, I told you about, right. There are crystalline blocks, as you can clearly see, these blocks are crystalline blocks, and you can also have amorphous blocks also. This is a crystalline block, you can see that the order arrangement of the chains, and in between you have amorphous structures or disorder structures. You can also have completely amorphous or total disorder structure in polymer also available, and that is why the polymers can have different kinds of properties depending on the type of structures present. Well, then you talked about composite material. I will not discuss more about it, because they are heterogeneous structures. They can consist of more than two or more than two different elements, and that can combine and to give you very interesting set of properties: high strength, stiffness, give resistance, even lightweight, everything is possible. And depending on the different arrangements, polymer can be laminar or layer structures, or they can be also particular structures or fiber structures possible. All kinds of different kinds of arrangements one can do to create different composite structures, so that material can provide you better properties. So, finally, we started discussing about the properties of materials, and we started discussing about mechanical properties, because that is the primary property required if you want to use this any material for structural applications. For any component which is used as a structural applications, the mechanical properties are the significant ones which to be used for design of such kind of structures, and material properties are considered for design of these kind of structures. So, you know why we should be talking about properties, because service condition to which components will be subject to must be compatible with the material properties, otherwise component will fail without giving much performance. And secondly, there are many manufacturing processes will require the mechanical properties or physical properties to be known beforehand. Without knowing these properties, you cannot select particular manufacturing process or route for preparation of this kind of materials or this kind of structures. So, that is why the understanding the properties are very important in a system like us. And you know, when you talk about mechanical properties, majority of these subjects are covered in this book by George E. Dieter, Mechanical Metallurgy. It is also available, not a very expensive book, but for the sake of your understanding, I will describe most of these things in a brief manner. If you really want to go into details of these aspects, please refer this book. You know, mechanical properties has to be discussed in terms of loading condition, whether it is a tensile, compressive or shear loading. Tensile loading is something which will pull the material apart, right, along certain directions. Compressivity means you will press the material to have some kind of a deformation, and shear means just like a application of shear forces. And you know, shear leads to change of shape of the material, but tensile and compressive tens might not lead to change of shape, and it can lead to size or the dimensions of the sample to be changed, but shape may not be changed. But in case of shear, the shape is changed, and the shear strain is dictated by this angle theta, which is causing the change of the shape of the material. Shear is very important in material synthesis by mechanical deformation processes. So, how do you measure the mechanical properties? By using a tensile testing machine, which is popularly known as a UTM or universal testing machine. Let me write down that universal testing machine is what is used. So, that is what is basically you probably have seen in many of the laboratories. Why it is called universal? Because it can be used to measure many properties or many different types of mechanical properties of materials, different kinds of materials, metal, ceramics, polymer, alloys, you can use that. That is why it is called a universal testing machine or UTM. And most important parts of a testing machine is basically two things. One is the load cell, by which you apply the force or the load actually, and second is the extensometer, what basically measures the elongation of the sample. So, as you see, this next picture is much better. So, you can clearly see this is a sample, extensometer is attached to the sample, and as you apply load, material will start deforming. So, therefore, its length will change, and the change of length is measured by this extensometer. Load cells can be different types, and they provides this stress or rather load to the material during testing. So, what are the different parameters actually we normally measure? First and foremost parameter is the stress, because that is what is the indicator of material property. Strength is what you can measure by measuring the stress. There are different types of stress one can measure. First is the engineering stress, that is defined by S. S is equal to F by A0, where F is the applied load and A0 is the original area. So, let us talk about it. You see, this is the sample, as you can see here, and load is applied on the both the directions of the sample on the both sides, and that is given by the symbol F. It has a length, initial length L0, and initial area of cross sectional area is A0, okay, initial cross sectional area before you start applying load or start deforming it actually. If you apply load, it may not deform plastically, but elastically it will deform. That is why I am talking about this. A0 is before it start plastically deforming. So, that is called original area, and after deformation the length of the sample or specimen will increase, and let us say it become L, and the original area has changed now to A0. Basically, it is a material, you cannot change the total volume of the material deforming, right. So, volume is equal to area into length. So, A0 L0 will be equal to A0 L0 will be equal to A and L, because that is the volume, that is constant, right, that is obviously must be constant. Or other hand, we can write down A by A0 is equal to L 0 by L from this equation. You can clearly see it is possible to write that. What about strain? Strain is defined as a change in length divided by original length, that is called engineering strength. Delta L is the change in length and L 0 is the original length, that is what is called as a engineering strength. So, engineering stress and engineering strain, please keep it in mind, they are basically used to measure the strength of the material as well as the deformation of material conventionally, and there we use original area and original length at the denominator. Well, how does the stress strain curve look like? That is what is shown in this slide. So, you can clearly see initially there is a portion called elastic portion, where stress is proportional to strain, or rather Hooke's law is applied. All of you should know Hooke's law. Hooke's law, stress is proportional to strain. Stress is proportional to strain. So, stress is equal to a constant multiplied by strain, and this constant is known as a Young's modulus. Young's modulus. You should know this. This is basically school physics, and you can see that the original portion of this stress strain curve, sorry, initial portion of stress strain curve is a straight line that follows this Hooke's law, and after a certain level of stress, material will start permanently deforming. That is what something called as yield stress. Yield stress is what? The stress at which materials start permanently deforming. That means, if you remove the stress after this or above this value of stress, material will never come back to its original shape and size. But below this, within the elastic limit, within the limit in which Hooke's law is applied, if you remove the stress, strain, material will go back to original shape and the size. That is the difference between elastic strain and the plastic strain. Elastic strain can be completely recovered, but plastic strain can never be recovered. So, that is why the curve starts showing nonlinear behavior after it reaches yield strength. You can see that it has become nonlinear here, and then it reaches a maximum stress, after which it falls, stress level falls. Okay, and this maximum stress is called as a tensile strength or ultimate tensile strength, and the final stress is called the fracture stress, at which the material is completely fractured. So, therefore, between initial and this maximum stress, you have a uniform strain, and above which you can have a non-uniform strain. Why? Because something happens at the top or the highest value of the stress, that is at this point, something happens here, which we will discuss in a very soon. So, something which is very peculiar happens above the stress level beyond this point. So, these parameters one should understand: yield stress, tensile stress, fracture stress, as well as uniform strain and Hooke's law. Very well one should know, because these are the parameters which will be used to design new materials using machine learning. Well, if I have to put it in a very nice picture, which is schematic, remember that this may not be the actual one. So, this is the elastic region in which Hooke's law is valid, and it reaches yield stress, materials start deforming plastically, and that is why you see the nonlinear nature of the curve. So, stress strain curve, and the maximum stress is called tensile stress or tensile strength. Fracture is happening at this point, that is called fracture stress, and this is known as a plastic region, where deformation is plastic type, not elastic type. Many times the yield point y may not be distinctly visible on the stress strain curve. Many non-ferrous metal like aluminum, titanium, they do not show very distinct yield point on the stress strain curve. So, we can determine that by putting a 0.2% offset line. What you do? You take 0.2% strain. So, you get this point and then draw a parallel line with respect to the initial stress strain curve. Wherever this parallel line will hit this nonlinear portion of the curve, that is what is determined as a proof stress. Proof. It is no longer called as a yield stress, it is called a proof stress. Pain is always problematic. So, it is called a proof stress. this point where it cuts, and it may not be same as the yield stress, but you cannot determine the yield stress because in the curve, measure curve, you do not see a demarcation between elastic and the plastic region. You have a problem to handle, and that problem can be sorted out by simply drawing a line parallel to the initial portion of the stress strain curve at the offset strain of 0.2%. That is what you do. So, then you can determine the proof stress that will be used as a parameter to design materials. Well, everything is shown here in this chart. This is very important. You can clearly see the stress is F by A0, strain is delta L by L0, and this is uniform elongation, necking. I told you that something happens here, we talk about now, and fracture. So, yield stress is somewhere there, that is actually 0.2% offset. You can see a parallel line has been drawn with respect to the initial linear portion of the stress strain curve. A parallel line is drawn as offset of 0.2% strain, and this cuts this curve at yield point, and you have ultimate tensile strain or tensile stress. Many people say UTS, many people say TS, but it is basically the highest portion of the highest point of the curve. So, offset is taken as a 0.2%, that is 0.002. 0.2% is nothing but this divided by this. So, it becomes 0.002 strain. So, these are the parameters which are important: yield strength, state at which the plastic deformation starts to occur, Young's modulus, slope of the linear elastic portion of the curve, UTS, ultimate tensile strength, is the maximum load divided by the A0 or initial area, and sometimes yield stress offset, this is 0.2%, and that is basically called as a proof stress. So, how this tensile, during tensile test the sample actually looks like. So, you can see 1 to 6, there are 6 defined schematic pictures I am showing you. So, one is basically has a dimension of L0, and then you pull it using some force, started elongating, and at some point it starts forming a neck in the sample, and that neck is where the deformation then is concentrated. So, till before this deformation is uniform along the sample, everywhere it happens same, but the moment it starts necking, the deformation is concentrated on this portion. No further deformation happens on this part of the sample. That is why it is called non-uniform elongation or deformation, and this starts happening at the highest stress. Okay, I can go back and show you. So, at the highest stress you can see here at this point this necking starts happening. Why does it happen? This things can be discussed. This is there nicely in the book of George Dieter, mathematical analysis or graphical analysis, everything can be understood, but this is exactly what happens. Now, the question is, after this neck slowly elongate and it fractures. So, that is what is shown in the 5 and 6. So, this is in a nutshell what will happen if you do a tensile test of any ductile sample. Brittle sample will fracture without any having any necking also, and this is shown again much detailed manner, the nature of necking and everything corresponding to the stress strain curve. As you clearly see that this figure shows final shape of a standard tensile test sample. Standard tensile test sample is basically look like a dog bone sample. You must have seen the kind of dog bone in your life. Sample geometry is exactly like that, and then you can actually deform it, and that is why necking happens and it fractures. Okay, so, more detail of the neck. Once the neck forms, the deformation localized at the neck, you can see there is a diffuse neck formation. You can also have a localized neck possible, and there the deformation will concentrate on this portion. There will be no further deformation happening here or there on this side of the sample. Well, how do you measure ductility? Ductility can be measured as a plastic deformation of a material before it fractures. So, first is the elongation to fracture, that is nothing but the final length minus the initial length divided by the initial length into 100, and percentage elongation is affected by the gauge length at L or L0, right. Short specimens will show higher values, that is why L0 has to be specified when you measure percentage elongation. But other hand, there is another parameter which can be used to measure ductility, that is called percentage reduction area. This is nothing but A0 minus F divided by A0. A0 is the original cross sectional area, AF is the final cross sectional area, and this has no specimen size effect. whether you use big specimen, small specimen, this value will not depend on that, but elongation will depends on this. So, hopefully you have understood the strength and the ductility part, right. So, we will discuss further on these aspects in the next portion of the lecture. So, let us stop here and we come back, we talk more about tensile deformation in the next part of the lecture.